Okay, we are module, I don't know why I wrote 14 there, module 18. Okay, which in looking at this module, it looks like a lot of stuff that you did in Algebra 2. So hopefully it's a little bit of review for you. If you have your interactive notebook, you might even want to dig that up because there are a lot of things from that here. Okay, we're going to start with transforming the graph of a natural exponential function. So it sounds scarier than it is. Natural log, if you guys remember, our natural exponents, the base is e. Okay, and e is kind of like pi, where it is a constant. There's a number. If you go on your calculator, there above the division sign is the e button, and you can type it in. E is 2.718281828. It doesn't stop. Okay, so it's a non-terminating decimal there, just like pi is. Okay, so that's what e is. So we are going to start with just your parent graph, and then we apply all the transformation rules just like we always do, okay? So your parent graph of y equals e to the x looks like this, okay? And there's always two really important points. The first one is if x is 0, then y would equal e to the 0, which is 1. Okay, and then the second one would be when x is 1, y is e. So I apologize, this isn't to scale, but there you go. There's your two important points. And it also has an asymptote. The x-axis is the asymptote. Okay, so y equals 0. And then these questions are also going to ask about the domain and the range. So on your parent graph, the domain is all real numbers, so negative infinity to infinity. And your range is going to be only positive values. So 0, and not including 0, because our asymptote is at 0, right? So it's never going to actually hit 0 to infinity. Okay? So we need to make sure we have that written down somewhere in your notes. Okay? So you can kind of keep referring back to that. So they ask that you, in this problem that I have brought up as an example, they give you this graph. Okay, and then so I guess maybe you don't need it in your notes, but I would suggest it. Okay, it says transform it to make the graph of y equals negative e to the x minus 6. Okay, and then it also wants you to give the domain and the range of that. So we know that this negative flips it or reflects it over the x-axis. Okay, and then this negative 6 moves it down 6. 6. Okay, so we're going to do that with, I think in Alex, they only ask you, you only have to do 1 point in the asymptote, I believe. Okay, so we're going to take that point at 0, 1. Okay, that was on our original graph at 0, 1. We're going to flip it over the x-axis, so we're at 0, negative 1. And then we're going to shift it down 6 units. So we actually end up at 0, negative 7. Okay, now your asymptote is at y equals 0. Flipping that over the x-axis doesn't do anything. All we need to do is shift that down 6 units. Okay. And then we have to think about what this whole graph would look like, flipped over the x-axis and then shifted down. Okay, so it's going to actually look like this. That would be our graph. All right. So then our domain here, I'll give you a hint. It's always going to be all real numbers for domain. Okay, and then your range, it's always going to be parentheses. And you just have to figure out the lowest to the highest, right? So this one, the lowest that we go all the way down to negative infinity, and the highest would be at negative 6. Okay, so that's how we would transform the graph. Okay, know your parent function and also know how to apply the transformations. Okay, let's get the next problem here. The next one is graphing, more graphing, so we'll get a little bit more practice with this. We have graphing an exponential function and its asymptote. and it's the form f of x equals a e to the x minus b plus c. Okay, so again, we have our parent function that I drew above. In this example, they want us to graph g of x equals 2e to the x plus 4 minus 4. Okay, so we've got a lot going on there. What they encourage you to do, and what I think Alex needs, is it looks like they want you to get 2 points and the asymptote. Okay, so the good news is this tells you your asymptote. Okay, we're going to move our graph down 4 units. So the asymptote that was at y equals 0 is now at y equals negative 4. Okay, and that will always be true. Whatever that number is on the end, that's where your asymptote is. Okay. Now, the next thing we need to do is figure out what makes the exponent 0. Makes exponent equal 0. And if the exponent is x plus 4, that would be when x is negative 4. Okay, and the reason that we choose 0 is because if that exponent is 0, e to the 0 is 1, and that gives us some numbers that we can work with pretty easily. So that's what we want to do. G of negative 4 then would be 2e to the negative 4 plus 4, and our whole goal there was that that's 0 minus 4. Okay, and then again, the whole goal there is that that is 0 because e to the 0 is 1. So then we have 2 minus 4, which is negative 2. So when x is negative 4, we have the point negative 2. Okay, so negative 4, negative 2. Okay, now the next point that you want is when the exponent is 1. Okay, so the second piece here is what makes the exponent 1. Okay, so when would x plus 4 equal 1? That would be when x is negative 3. Okay, so g of negative 3 would equal 2e to the negative 3 plus 4 minus 4. And that would be e to the first power, so 2e minus 4. And you get to just leave it like that. So your point is negative 3, 2e minus 4. Okay, and you can just plot that right on Alex. You can type e in, I believe. Let me know if you can't. Okay, you can kind of get an idea of this. If you remember, e is between 2.5 and 3. Okay, so this is going to be between 5 minus 4 and 6 minus 4. So it's somewhere between 1 and 2. Okay, so when you plot it, I know in Alex you can just type in the coordinates too if you want to. I mean, you can do that. So you probably do need to do that, but you can get an idea of where it should be. Okay, if you were ever to have to do something like this by hand. Okay, so there you go. So it's your exponential graph. And if we go back to this problem, we know it's shifted to the left 4, down 4, and that 2 out front stretches it. Okay, so it's a little bit of a steeper graph. Okay, and there is no vertical asymptote on these. It kind of looks like it once it gets steep, but just know this growth keeps going up and to the right forever. Okay, so there's your graph. All right, so getting those 2 points in the asymptote is what Alex is going to want you to do. Okay, our next topic we have, and I remember doing this like in middle school. Just need a little refresher here. This is finding a final amount in a word problem on exponential growth and decay. dk. And I'm not a big fan of the way that Alex shows you how to do this. If you remember, you probably learned this with money, where the amount in the account is the principal, 1 plus the rate, and then t was how much time, how many times it had been. It's compound interest, okay? And so we'll just stick with the same formula. This is an initial amount. This is the rate. Make sure that it's a percent, so we divide by 100. If we're increasing, it's going to be positive. If we're decreasing, it's going to be negative. Okay. And then this is the time. Okay, and then this is the amount after time t. Okay. So in this example, it says a certain forest covers 3,800 square kilometers. Okay, and then it says each year the area decreases by 5.25%. Okay, what will the area be after 12 years? Okay, so we're going to mark this up a little bit here. First of all, this is going to be your starting amount. Okay, we're covering 3,800 square kilometers. Each year, the area decreases, okay, by 5.25%. So we're going to have negative 0.0525. Okay, so that rate is a percent. We divide it by 1,000, so it's 0.0525. And since we're decreasing, we make it negative, and that's R. T is going to be 12, and we're going to be finding A. Okay, so A will equal 3,800 times 1 minus 0.0525 to the 12. Okay, now in that set of parentheses, we're going to have 3,800 times 0.9475 to the 12. Okay, so what this means here basically is that every year 94.75% of the forest remains. Okay, 5.25% of 100% has left, leaving us with just 94.75%. And you're going to be able to use your calculator to do this. They do have you just round it to the nearest whole number. Okay, so on my calculator, I get 0.9, do 0.9475 to the 12th first. Okay, and that comes out to be about 0.5235. You know, leave it right on your screen and multiply by 3,800, and I get 1989.455459. They want the nearest square kilometers, so make sure you read the instructions carefully. Since we have a 4 after the decimal, we'll round down. 1,989 kilometers squared. Final answer. Okay? All right, let's take a look at the next one. Next we have converting between logarithmic and exponential equations. Okay, so again, this you might remember from Algebra 2. Log base B of A equals C. You might have written it using different variables. Okay, but you might remember the loop and swoop. So you take your b to the c equals a. Okay, and this is a logarithmic equation, and this is an exponential equation. Okay, so in this particular example that I have here, they want you to rewrite log base 3 of 81 equals 4 as an exponential equation. So the answer there would be 3 to the 4 equals 81. Okay, in place of b, I have 3. In place of a, I have 81. In place of c, I have 4. So I need to do b to the c equals a. Loop and swoop. Okay. And then they give me 8 to the negative 1 equals 1/8. Okay, so now we're going in the opposite direction, which I think is the trickier one for most kids. Okay, but this is B, this is C, and this is A. So we'll have log base B, so base 8, of A, of 1/8, equals C. And if you think about going back again and looping and swooping, we get 8 to the negative 1 is 1/8. There's your final answer. Okay. And by the way, keep in mind these expressions, checking the 3 to the 4th power is 81. 3 times 3 is 9, times 3 is 27, times 3 is 81. 8 to the negative 1 would be 1/8. Okay. So it's important too that you can kind of recognize how these exponents work too. So it's easy as that for that one though. Our next one is converting. It's very similar. It's just with natural logs instead of any base. Okay, so converting between natural logarithmic. So remember that means your base is e, and exponential equations. Okay, so back up when we had log base b of a equals c. If b equals e, then we'd have log base e of a equals c. Log base e is what we call the natural log, which is ln. It's actually French, logarithmic natural or something like that. I don't have a French accent, but the reason that some kids wonder why it's not NL for natural log, because it's not an English term. It's natural logarithmic or something like that. Okay, so the natural log of A equals C. Okay, so you just have to remember that when you see an expression that's written like this, that kind of hidden base that we don't see is E. Okay, just like you guys might remember too that if we have something like this, the base is 10. Okay, this is base E. If there's no little base listed and when it says the word log, then by default the base is 10. Okay. All right, so natural log of A equals C. There's your logarithmic form. And your exponential form would be e to the c equals a. Okay, so we can go between those two forms. Okay, so the first problem that I see on my screen is e to the y equals 6. All right, so it looks to me like c is y and a is 6. So we would go to the natural log of 6 equals y. And then if I think about my loop and swoop, e to the y equals 6, that's a good answer. Okay. The other problem they give me is the natural log of x equals 7 and asks to put it in exponential. So e to the 7 equals x. Okay. All right, let's take a look at another one here. Evaluating logarithmic expressions. Okay, so this one, we have log base 6 of 1/6 equals, and we're supposed to fill in the blank. Okay, and then we have log base 4 of 64 equals what? Okay, so we're supposed to fill in those blanks. So what you want to do is take it from its logarithmic form and go to the exponential form. Okay, so 6 to what power is 1/6? And then 4 to what power is 64? Okay, so here's the thing. We know that 6 to the 0 power is 1. 6 to the first power is 6. 6 to the second power is 36, right? And I could keep going and they keep getting bigger. If my goal here is a number that's less than 1, that means my exponent has to be negative. Okay, so don't forget about those negative exponents. 6 to the negative 1 would be 1/6. Okay, so that's going to be our answer. 6 to the negative 2 is 1/36, right? It's just going to be the positive ones, but the reciprocal. All right, so this answer will be -1. And then 4 to what power is 64? So again, 4 to the 0 is 1. 4 to the first power is 4, which means 4 to the negative first would be 1/4. 4 squared is 16, which means 4 to the negative 2 is 1/16. 4 cubed, so take your 16 times 4, and you get 64. Okay, which would mean that 4 to the negative 3 would be 1/64. All right, a lot of kids get those negative ones confused, but they're not. Just think about the reciprocal of the positive ones. Okay. All right, next we have translating the graph of a logarithmic function. So back to our graphing. Okay, they give you the graph of a function. So this one they give is log base 2 of x. Okay, and that parent function actually has an asymptote at the y-axis. Let me switch colors here. Y-axis. Okay, so at x equals 0 is an asymptote. I find these easier to graph if you put them in exponential. 2 to the y equals x. Okay, but just be careful then. That means, if I'm going to plug in a 0, that means y is 0, x is 1. Okay, so 1, 0. All right. If I want to make y be 1, then x is 2. So 2, 1. Okay. And these, if you remember, log graphs are just the inverse of exponential graphs. Okay, so they have a lot of the same properties, just everything's switched. Remember, your exponential graph looks like this. Okay, they're reflections over the line y equals x. I'm going to erase that so it doesn't get confusing. Okay, but they give you this. They give you this graph, and the point that they include on it is the 1, 0. Okay, 1, 0 is actually on every single logarithmic graph that hasn't been transformed. Okay, so log base 4 of x, the point 1, 0 would also be on it. Okay, so they want you to graph y equals log base 2 of x plus 1 minus 4. So all your transformation rules apply, right? This means left 1, and this means down 4. Okay, and so they want you to move that point accordingly. And I don't think they have you even worry about the equation of the asymptote or anything. Okay, so we take that point that's at 1, 0, and they just have you drag the graph left 1, down 4. There's where that point ends up. Okay, so it looks like this. That's all you have to do. All right, my next one. Now we're going to graph them. Excuse me. Okay. So we're going to, again, think about that parent function that I just drew up there because we're going to use them a little bit. Graphing a logarithmic function, and they call this basic. Okay. They want us to graph f of x equals 4 log base 2 of x. Okay. They want 2 points and the asymptote. Okay. So we go back up to the one that we drew up here, log base 2 of x, right? And the 2 points are always, you want to use when x is 1 and when x is 2 and get the transformation. Okay. So we are actually going to write this as y equals 4 log base 2 of x. Okay. And so what we want to do is actually take that stretch factor out and then use it later. Okay, so y equals log base 2 of x. Let me think here about how we want to do this. I'm trying to look at how they did it to see if there's any hints that they, like, sometimes they do things weird. Yeah, they just use different values of x. Okay. So what they tell you to do, okay, I'm going to back up a second here. Okay. I think maybe their way might be a little easier than I was thinking. So the base is 2. So use x values that are powers of 2. Okay, and you only need 2 of them. All right, so really what you can use would be 2 to the 0 and 2 to the first. So just use 1 and 2. Okay, I'll do one more example. You could also do like 2 to the 2, which is 4, but it's not necessary. Okay, the reason we can do that then, the log base 2 of 2, I'm sorry, I wanted to start with 1. Log base 2 of 1, right? 2 to what power is 1? Well, we chose it because it's 0. Okay, so when x is 0, when x is 1, log base 2 of 1 is 0, and we have the point 1, 0. Okay. Log base 2 of our next one that we're going to use, which is 2, is 1. And that's why we chose it. Okay. So when I plug in an x value of 2, log base 2 of 2 is 1. So y would be 4. Okay. And like I said, you only need the 2 points. But I'll show you one more. If we plug in x is 4, log base 2 of 4 is 2. So then we'd have 4 times 2, which is 8. So when x is 4, y is 8. Okay, so there's some points we can use. 1, 0, 2, 4, and 4, 8. 1, 0, 2, 4, and 4, 8. Okay, and there has been no shift left or right here, so your asymptote is still at x equals 0. Okay, so our graph, oopsie, didn't really go through the points there, but once you get your 2 points, it should look like that. Okay, I'm just going to check other problems here. Yeah, okay. The other type of problem that they're going to give you, okay, so this is one where we have a stretch factor. It looks like they're also giving ones with a shift, but just up. I don't see any that have been shifted left or right. Okay, so another example here. We'll do 2 for this one, so we get both types of problems. F of x is 4 plus log base 3 of x. Okay, the base is 3. So use 3 to the 0, 3 to the 1, 3 to the 2. Again, you only need 2 of them, but I'll show you with all 3 so that you can see. Okay, so we're going to use x equals 3 to 0, which is 1, 3 to the first, which is 3, and 3 squared, which is 9. Okay, so f of 1 would be 4 plus log base 3 of 1. So 3 to what power is 1? 3 to the 0. That's why you chose it. Okay, so log base 3 of 1 is 0, so it's 4. So we have the 0.14. F of 3, our next x value that we want. 4 plus log base 3 of 3, and this is 1. So we get 5. It's the 0.35. And then f of 9, 4 plus log base 3 of 9. Log base 3 of 9 is 2. 3 squared is 9, right? So 4 plus 2, which is 6. Okay, so we'll have 9, 6. Okay, and then when we graph it, that asymptote at x equals 0, we're only shifting up, okay, adding 4. So the asymptote will not change. Still there. Okay, in this section, the asymptote never changes. It's always x equals 0. Then we have our 0.14. We have our 0.35. And we'll have our 0.96. Okay, so there you go. Graph should look like that. Okay. All right, let's take the next problem. Okay. This one's really similar. Okay, graphing again, but they want the domain and the range. Okay. But same idea. It looks like the first one that came up for me has both a vertical and a horizontal shift. But same idea with plugging in numbers that are going to make this easy for you. So we've got the graph, domain, and range of a logarithmic function. Okay, so we have g of x equals log base 3 of x plus 1 minus 2. Okay, so our whole goal here with picking x values is that we pick x values so that x plus 1 can easily be, that log base 3 of that can easily be taken. Okay, so we want it again, if that can be 1, we're in good shape. So if x can be 0, then we would have log base 3 of 1 minus 2. So that'd be 0 minus 2, which is negative 2. Okay, so we want to make this equal 1, right? Or I should say 3 to the 0, 3 to the 1, 3 squared. Okay, so that would mean x equals 0 would make it 1. 2 would make it 3. And 8 would make it 9. Okay? So if I plug in 2, then I get to do log base 3 of 3 minus 2, which is 1 minus 2. And if I plug in 8, then I get log base 3 of 9 minus 2, which is 2 minus 2, which is 0. Okay, so same idea as before. Since it's base 3, we want to be taking the log of powers of 3. But we just have to keep in mind that we have to do x plus 1 to get there. So we can't just plug in 1, 3, and 9, right? We're going to plug in 0, 2, and 8, knowing that we have to add 1 to it. Okay, so there's your points. All right, and then as far as the asymptote goes, this transformation is down to, which doesn't affect the asymptote, right? A vertical line moved down 2 units is still a vertical line in the same spot. This one, it's left 1. Okay, so our asymptote is at x equals -1. And then our points are x equals 0, y is -2. X is 2. Oops, I'm going to run out of room here. Y is -1. And then x is 8, so it'll be way over to the right, 0. Okay, so this, oops, I'm totally missed that point there. Okay, but it should have this shape to it. Okay. So there's your graph. One thing that we have not talked about yet is the domain and the range. So if you remember when we did domain and range for an exponential, the domain was all real numbers. We have logarithmic, so the range is all real numbers. So you're going to see that for every single one of these problems. The range is all real numbers, okay? It goes all the way down to negative infinity very quickly. It goes up to positive infinity very slowly, okay? Your domain, you got to take a look at your asymptote, just like we did with exponential, but the asymptote was horizontal. Now your asymptote is vertical, okay? So -1, and we're going to positive values, so -1 to infinity, okay? If we were on the other side, we'd be negative infinity to -1. All right? Okay. Next, we get some fun ones coming up here. Okay, basic properties of logarithms. You definitely want these somewhere in your notes. Okay, so, and I want to get them written out the same way your Alex does. Okay, we have the logarithm of a product. Okay, so log base A of m times n. Okay, so like two things multiplied together, doesn't matter. They could be numbers, they could be entire expressions. We'll see it in examples. Log base A of m plus log base A of n. And I remember in Algebra 2, you guys do this where they give you a bunch of examples and you try to find like the ancient secret of the puzzle and you kind of figure these out. Okay, logarithm of a quotient. So product is a multiplication problem. Quotient is the answer of a division problem. Log base A of m over n is just what you would expect probably, hopefully. Log base A of m minus log base A of n. Okay, and then we have our logarithm of a power. And that's log base A of m to a power. If you remember that, remember you could pop the power out front. So P times log base A of m. Okay, so those are your properties that we need. Okay, And so they give you 3 problems that use these properties. The first one, log base 3 of 8 plus log base 3 of 5 is log base 3. Notice in order for any of these to work, they all have to be in the same base. So we couldn't do like a log base 4 in here, okay? But we fill in the blank. The second one, log base 8 of what? Plus, oops, minus actually. Minus log, come on. There we go. Log base 8 of 11 is log base 8 of 5 over 11. Okay, and then the last one they give you, log base, let's go, log base 7 of 9 is 2 log base 7 of what? Okay, I'm going to fix my 9 because I know everyone always complains that my 9s look like G's, and that one definitely looks like a G. Okay. All right, so in the first one, we're in the properties that we're using go right in the order of how we wrote them, okay? Log base 3 of 8 plus log base 3 of 5, that'd be log base 3 of 8 times 5. So that one would be 40, okay? And then we have subtraction. So log base A of m minus log base A of n would be log base A of m over n. Okay, so to get 5 over 11, that first blank would have to be a 5. Okay, and then C, we have to figure out this 9 can be written as what to the second power so that we can take that 2 and put it out front. So it's got to be 3. Okay. All right. Next, we're going to do all kinds of fun puzzles with those. Okay. So we're going to expand logarithms using those properties. So expanding a logarithmic expression. We have problem type 1. Okay, so we're supposed to use the properties of logarithms to expand log base, so if they don't give you a base, it's 10, x over z to the 9th. Okay, so we are supposed to do what's called expanding this. And the goal here, and they write it out for you too, is each logarithm should involve only one variable and should not have any exponents. Okay, and it also says that you can assume that all variables are positive. All right, so you kind of have to think about what we could do first here. So we have a numerator and a denominator, so we want to split those up. So we can rewrite this as log x minus log z to the 9th. Okay, so we're using that quotient rule. Okay, and then we can use that third with the logarithm of a power and take that 9 out front. And that's going to be actually your final answer. Okay, I like these, so I'm going to do another one. I just think they're fun. The next one we have, oh, it's really similar. Looks like these are all going to be similar. So it's okay. We have other problem types, so you don't have to worry. If you found that fun, here's another one. So we're going to do expanding again. These were like one of my favorites when I was in pre-calc. Problem type 2. Kind of looks like stoichiometry, doesn't it? When you're in calc or in chemistry. It looks like it. I mean, it's not a similar topic, but anyways. Okay. This one we have the log of the square root, the big square root of yz cubed over x to the fifth. Okay, so we got to deal with that square root first, right? Okay, and we didn't have any properties that used a square root. Okay, but we know that we can write that square root as a power. It's 1/2 power, the square root is, right? Okay, so now we can put that 1/2 out front because of our logarithm of a power property. And now we get to split up what's left. Okay, so first we're going to deal with that, separating that numerator and the denominator. We're going to put this 1/2 outside of everything. Okay, so be real careful with your parentheses and stuff here, but we'll have log of yz cubed. Once you get good at these two, you can kind of combine steps a little bit. Minus the log of x to the fifth. Okay. Now we can split that yz cubed also, and that's what I was just kind of saying is you could do that right off the bat. Log y plus log z cubed minus log x to the fifth. Okay. All right, so now we've got them separated, so there's one variable in each logarithm. We're going to pop those powers out front. Nothing on the log y, but we can do it as 3 log z minus 5 log x. Okay, and then the final thing that they want us to do is get that 1/2 distributed. We'd have 1/2 log y plus 3/2 log z minus 5/2 log x. And that's your final answer. And I just want to see here. Okay, we'll do another one in this one. Okay. So the next one we have is the log of x to the fifth over the cube root y squared z. There's a lot going on here, so be careful with all the steps you're taking. Okay. Now the kind of like the outer function, the thing we're going to do first is separate the numerator and the denominator. So I have log x to the fifth minus log cube root y squared z. Okay, and that cube root, remember we can write it as the 1/3 power. So we'll have y squared z to the 1/3. Okay, so now we have two exponents here that we can pop out. So we can have 5 log x minus 1/3 log y squared z. Okay, and now that first 5 log 5, we're done with that. Okay, but we can keep working. We got to separate the y and the z more. Okay, so we're going to have minus 1/3 log y squared plus log z. Okay, and now we can take that squared out. So we'll have 2 log y plus log z. And the final thing that we're going to do is distribute that 1/3, but let's make sure that we get that it's negative. Okay, so your final answer will have 5 log x minus 2/3 log y minus 1/3 log z. Okay, and that should be your final answer. Okay, all right, we have a problem type 3 with this one. Okay. So this one, we have log 7 x plus 6 cubed over square root x to the 5th. Okay, and I think it's just, I'm not really sure what makes this type 3. I think it just makes it a little more complicated, I guess. Okay, but same steps. Like, we're going to split up that numerator and the denominator. Log 7 x plus 6 cubed minus log square root x to the 5th. Okay. Now we're actually going to split up, since the exponent is only on the x to the 6th, so we can't put it out front. Okay, what we need to do is split that log 7 plus log x plus 6 to the 3rd. Okay, and the other thing that we're going to do is write log x to the 5th to the 1/2. Okay, we'll take that root and make it the 1/2 power. Okay, so then we have log 7 plus 3 log x plus 6. And as much as we might want to, you can't split up that x plus 6 at all. If it was x times 6, you could, right? But you can't when it's addition. And then we got some exponents going on here. Remember, your power of a power, that's just x to the 5/2. Okay, so once we pop that 5/2 out front, we're done. So we have log 7 plus 3 log x plus 6 minus 5/2 log x. That's it. Okay, we'll do another one of those, mostly because I like them. But also just make sure that we're getting all the problem types. Let's see, next one looks pretty similar. Okay, here's a different one a little bit. This next one is log big square root x plus 4 to the 5th over x cubed. Okay, so here we go. Ready? That square root needs to be a 1/2 power. So that we can put it out front. Now we can split that guy up with subtraction. And we can get some of those exponents out front. Starting to get messy because my Chromebook's getting slow. Let's see, 5 log x plus 4 minus 3 log x. And then we can finish up by distributing that 1/2. Okay, there we go. And actually, for some reason, this is the answer that they're showing on Alex for me. So they might take it, but it seems like in all the other ones, they wanted you to distribute and give that as your answer. So you can see what they do. All right, if you thought that was fun, now we get to go the other way. Okay, so now it's going to be all expanded and we put it together. So we're going to write an expression as a single logarithm. Okay, so reverse of what we just did. So in this one, we have 1/3 log base 7 of y plus 4 log base 7 of z minus log base 7 of w. Okay, so the first thing we're going to do is put our exponents back on the bases. Okay, so we're going to have log base 7 of y to the 1/3 plus log base 7 of z to the 4th minus log base 7 of w. Okay, now we're going to put those first two together. So log base 7 of y to the 1/3 z to the 4th minus log base 7 of w. And then we can rewrite that as log base 7 of y to the 1/3 z to the 4th over w. So the reverse of what we had been doing before. Now we get to put it all back together and make it nice and compact. Okay. And these all look really similar. Let me get one. That's a little tricky. That might trip you up a little bit. Oops, and I skipped past it. Hold on a second. Okay. This one's a little different. So the next one we have is 5 log base a. So they don't give you a number for whatever reason. Don't let that throw you off. Of y minus 1/3 log base a of x plus 7 log base a of w. Okay, so again, first step is pop those exponents up, okay? Log base a of y to the 5th minus log base a of x to the 1/3, okay? Plus log base a of w to the 7th. All right, so now we do the first two together, and it's subtraction. So it's going to be log base a of y to the 5th over x to the 1/3 plus log base a of w to the 7th. Okay, so now we combine these. The w to the 7th will be in the numerator. So y to the 5th, w to the 7th over x to the 1/3. Okay, and I think we got one more topic here. Change of base for logs. This is actually pretty straightforward, and you might remember it from Algebra 2. Okay, so change of base for logarithms. Okay. If you remember, if you have log base a of b, your calculator, depending on what type of calculator you have, only operates in base 10 or base e. So if we have something like log base 7 of 3, you can't just type that in your calculator. And like I said, some of the newer ones, I think now you can, but we're going to just leave it as is because I think Alex will even ask you like what the change of base is. So this is the same, okay, this is a property here, is log base c of b over log base c of a. And the good news is you can pick c, okay? C, most conveniently, would be 10. Okay, the other one that it might be, C equals E, also works on your calculator. Okay, so if we have log base 7 of 3, we can do is log base 10. Remember, you don't write the 10 when it's base 10, of 3 over log of 7. And on my calculator, when I do log 3, I get 0.47712125547 to a decimal or 10 decimal places. When I do log 7, I get 0.8450980. Okay, and that will give me an answer. And in fact, I can just do it in parentheses on my calculator screen. I can do parenthesis log 3 divided by parenthesis log 7. Okay, so log 3 divided by log 7. It gets to be, they want you to round it to the nearest thousandth. So that's 3 decimal places. So 0.56, it's 457. Okay, so to the thousandth place, it'd be 0.565. Okay, and that's all you got to do. I can do one more example if you want. I don't think these get too tricky at all. Okay, the next one, well, I don't even need to pick one from Alex, I guess. I could just log base 9 of 4. Okay, log base 9 of 4 would be log 4 over log 9. And I can do that on my calculator. And I get 0.6309297536. So it's in the nearest thousandth, 0.631. Come on. And there we go. Okay. And that's it for module, whatever module we're on. 18, I think it was. Okay. All done.